Hi everyone. Chris and Daniela, thanks. For organizing this thing. So I'm going to talk about homomorphic encryption as the slide indicated, but let me just give like a very short exposition to this whole morning. Daniel and Vinod and Hotek and myself was sort of trying to figure out a way to tell you this story about all these new developments, and I'm going to start by talking about fully homomorphic encryption. But what Daniel and Vinod and Hotek are actually going to show you is that this fully homomorphic encryption scheme, which is quite wonderful by itself, can actually be seen as just one face of a really beautiful mathematical structure that can be used to achieve other exciting cryptographic goals. So for the next 40 and some minutes, you can just forget about this whole thing and just think about homomorphic encryption, and then we'll see how it fits into this larger framework. So I imagine that most of this audience have at least sort of seen what this, at least the talk about homomorphic encryption or heard about it. But if you do need a motivating example, you can think about this problem of outsourcing computation, where we have this weak device that wants to use a strong server in order to compute some function, and there are many real-life examples as to why we want to do it. And also some fake life, just for cryptographic purposes, reasons why this would be sought after. More formally, we have a client that has an input, and we have a server that knows how to compute some function, and we want the client wants to use the server to compute this f of x. So the way it's normally done, we're just going to send the input to the server is going to compute and send us the output back. And this works great so long as we sort of don't care about the server knowing our input. And you can think about some cases where our input, the x, is actually private, and you don't want the server to learn anything about x. So that's the problem of privately outsourcing computation. And we would like to allow the server to perform processing on the input in a blindfolded manner. And sort of the most natural way as cryptographers to think about sort of sending information in a way that does not reveal its content is using encryption. So we would like to take our input, encrypt it, and send it to the server. And now the server, well, just by the security of the encryption scheme, should learn nothing about the contents, about x itself. But we still want to allow the server to compute on this information. So obviously the server does not know x, so it cannot produce f of x itself. But hopefully it will be able to sort of work on this encryption of x and produce some value y that we can decrypt locally to get the value f of x that we want. So really sort of this magic that we're looking for is what we call a homomorphic evaluation function. And this is a function that takes a description of this procedure f that the server wants to carry out, and an encryption of the input, and produces an encryption of the output. So we want to get a way to go from encryption of the input to encryption of the output using only public information, so without the server learning anything about the input x itself. And this leads us to the actual definition of fully homomorphic encryption. So it's an encryption scheme, and we're thinking about, say, the public key setting. So we're going to start by a key generation process. So we're generating a secret key and a public key for our scheme. And the public key can be known to anyone, and in particular to the server. And like any public key encryption scheme, we're going to use the public key to encrypt our inputs. So in this case, the party that does both the encryption and the encryption is the same person. And this is actually quite an interesting case by itself. We can also allow, like the normal public key setting, to have a third party that does the encryption. So the encryptor and the decryptor do not have to be the same person. And then the server, he knows the function that he wants to compute, and he knows he has the encrypted input. So he will be able to execute a homomorphic evaluation procedure and obtain this value y. And our correctness requirement is that if someone encrypted an input properly and the server executed this homomorphic evaluation properly, then when we decrypt, we really should get the value f of x that we want. So this is what homomorphic encryption is supposed to provide. And of course, in addition to correctness, we also want privacy. This is sort of why we're here. But the input privacy turns out to be defined in sort of the most obvious way. This is just the same as semantic security for any other public key encryption scheme. So we don't need to worry too much about the definition of security. So we just want to say that for all x, an encryption of x is going to be computationally indistinguishable from an encryption of 0. And this should, of course, hold true even for a distinguisher that knows the public key. So this is just standard semantic security. The sort of gimmick of homomorphic encryption is more in terms of functionality, being able to perform these homomorphic evaluations. So if you think about it for a bit, you can see that if this is all that we want, then this is very easy to achieve just by sort of cheating. I can just define this homomorphic evaluation as a function that sort of does nothing. It just outputs its input. So I can take my y to just be f and the encryption of x themselves and sort of push all the work down to the decryption and define a decryption process that sort of takes a tuple of function and ciphertext and first of all decrypts the ciphertext and then evaluates the function. Therefore, sort of going back to the solution of doing everything locally. And sort of just to prevent this degenerate solution, we're going to require a condition that's called compactness. And there are many ways to define it. But for now, just think about it, or not for now, for this talk, just think about it as requiring that this value y, the output of the homomorphic evaluation, should not depend, its length should not depend on the function f. So it doesn't necessarily have to look exactly the same as a fresh encryption of f of x, but it should not grow as we change the function that we want to evaluate. So this is homomorphic encryption, and when we talk about fully homomorphic encryption, what we mean by fully is that we want to allow the server to evaluate any function that it wants. So we want this correctness condition to hold for any efficiently computable f, and actually you can even extend it to inefficiently computable so long as the server has the sufficient computational power to execute the function. And sort of this seems like a pretty formidable task to allow correctness for any possible function, but we already know how to take these functions and represent them as circuits, and then break those circuits into gates, and getting homomorphism with respect to these tiny building blocks is going to give us correctness for the whole thing. And indeed, our task when constructing homomorphic encryption schemes will be to get homomorphism for a universal set of gates. So in particular, one easy to handle universal set of gates is just a NAND gate. We know that any polynomial size circuit can be made to be composed of NAND gates at all, NAND gates and nothing else. But another perhaps more popular choice is to think about sort of a more arithmetic case and think about addition and multiplication gates. So actually, if we get addition and multiplication over really any field or even any ring, this should be good enough. Because, well, we can think about just having, let's say we have addition and multiplication, and we can just represent the wires of our circuits just as the values 0 and 1. So we will not even use all the values that this field allows us. And then multiplication is really going to correspond to the binary AND operation. And we can always represent binary NOT by the 1 minus x function. And therefore, if we get addition and multiplication over any ring, this is going to give us what we want. So this is going to be our goal when we want to construct homomorphic encryption. And just to say that while fully homomorphic encryption is our ultimate goal, we're actually going to be pretty happy with what's called a leveled fully homomorphic encryption scheme. So in a leveled fully homomorphic encryption scheme, we actually don't sort of commit to being able to evaluate all functions, but rather only bounded depth functions. And what we want is actually to be able to produce a scheme for any depth bound that we can get. So we sort of know in advance what's the most complicated or the deepest circuit that we will want to evaluate, and then we can produce a scheme that supports this functionality. So this is what fully homomorphic encryption is all about. This is what we're going to talk about in this talk. And of course, I cannot mention fully homomorphic encryption without sort of mentioning its sort of this great story. Rivest, Edelman, and Dertouzas came up with the idea of fully homomorphic encryption back in 1978. So this is really just the dawn of public key encryption. We didn't even have, I guess, semantic security at the time. I still sort of this wouldn't it be great idea came up, but it was really far from being achievable, and that remained the case for many years, despite many attempts, until this great breakthrough by Craig Gentry, which was a grad student at the time, in I guess late 2008, and he showed the first candidate, the first scheme that actually sort of supported this functionality and security, and this sort of made the whole field really sort of bubble in steam, and there were a lot of developments and a lot of great ideas. But in this talk, I'm actually only going to present, I guess, the most modern approach to fully homomorphic encryption, and this is this approximate eigenvector method presented by Gentry, Sahai, and Waters, and this was only from 2 years ago, as Chris mentioned. And the basic idea is the following. So we want to get this homomorphic evaluation to work for, say, addition and multiplication. And we noticed that if we have two matrices, C1 and C2, that have the same eigenvector S, and in C1, this eigenvector corresponds to eigenvalue M1, and in C2, it corresponds to eigenvalue M2. Then, if we add these two matrices, then this the sum of the two matrices is, well, it's going to have the same eigenvector S, and the corresponding eigenvalue is going to be the sum of these two values, M1 and M2. And if we multiply these two matrices, and actually even if we multiply them in the opposite order, this is a non-commutative operation, then the eigenvalue that corresponds to S is going to be M1 times M2, and we're actually going to sort of see it in a little more detail. But this sort of basic idea sort of gives rise to the following, I guess, meta scheme. So why don't we have our ciphertext be matrices? And the message that is encoded, that is encrypted in the matrix, is going to be an eigenvalue that corresponds to an eigenvector, which is secret. So, you know, at least hopefully, if this eigenvector is secret, then perhaps the message is hidden. But if I know what this vector S is, then I can recover the message. So if we had an encryption scheme with this high-level structure, then we would be able to do these homomorphic operations. So just to pick some field to work with, let's say that we work modulo q for some integer q. So we'll get homomorphic for addition and multiplication, and this will give us full homomorphism. And this seems to be, again, so this is a great high-level outline, but it's really easy to see that it's insecure because it's pretty easy to compute eigenvectors of a matrix. So the secret key is not going to be hidden in the strong way that we want it to be hidden for secure encryption schemes. So at least if you want to sort of get the sort of utmost level of security that we want, semantic security, this seems to not be the best idea. So it's tempting to just sort of toss it and try something else. But actually, you can think about just maybe slightly tweaking this idea. So what if my secret key is not really an eigenvector, but it's approximately an eigenvector? And by that I mean the following. So first of all, let me sort of warn you that I'm going to use, instead of the secret key being an eigenvector of the ciphertext, it's going to be an eigenvector of the transposed. And this just means that I'm multiplying on the left instead of on the right. I hope this notation is not too confusing. It will be helpful for the rest of the morning. Instead of, what we say when we say approximate eigenvector is that when I take the secret key vector and multiply it by the ciphertext, I'm going to get message times secret plus some small noise, or in other words, it's going to be approximately equal to the message times secret. So if there was an equality here, then this means that really S is an eigenvector with eigenvalue M. But we're sort of relaxing this condition, and this is sort of the approximate eigenvector idea. And for now, take it on faith that when we are able to achieve this this schema, then such ciphertexts are going to be decryptable, so long as this noise vector has a very low norm, and this norm needs to be much smaller than q. Q is the modulus that we work over. So we would like to see if just relaxing this perfect condition to a relaxed one is still going to give us the homomorphism that we want. So let's see how this works. So let's say that we have two of these ciphertexts, C1 and C2, such that C1 equals to M1S plus E1, and C2, well, just the equivalent. And let's say that we start with noises that really are really small, much smaller than Q. And our goal, remember, we have this server that has an encryption of the input, so encryption of all these bits of the input, and it wants to execute a circuit. So in particular, we want to go from two ciphertexts C1 and C2 to an encryption of their sum, to be able to go to an encryption of their sum, and to an encryption of their product. So in order to get the sum, well, let's just try to add these two matrices. It seemed to work before when we didn't have noise, so let's see what happens. So let's say that I generated C_add as C1 plus C2. Let's see what happens when I try to decrypt C1 plus C2 with the same secret key that worked for C1 and C2. So this just gives me S times C1 plus S times C2, okay. And I'm just going to open these two expressions based on these what we know on C1 and C2. And of course, we only do it in our head. The homomorphic evaluator, the server himself, does not know S, but we should check that really this homomorphic evaluation means something. And what we get is really M1 plus M2 times S plus E1 plus E2. So we really get something of the same form as what we start with, which is great, which means that we really get this homomorphic correctness for addition. But our new noise is the sum of the old noises, so the noise grows a little. This is perhaps a little worrisome, but if we start with noises that are really small, then at least for a few operations we're going to be okay. So at least it's going to give us some level of homomorphism. Okay, so that's good. Now let's see what happens when we try to multiply. So again, before we said, well, maybe for multiplication we're going to take C1 times C2. Let's see what this gives us when we try to decrypt. So S times C1 times C2, I'm going to try to see what happens. So S times C1 is just M1 times S plus E1. This comes from here. And this multiplies C2. Open the parentheses. You get M1 C2S. So remember that the M's are scalar. So I'm pretty freely moving them from side to side of these vectors and matrices and so forth. So the M's are scalars, but everything else is non-commutative.
It says C2, right?
That's what? Where?
C2 instead of C2S.
Right, right. And again, this should be S times C2. Thanks, Chris and Duncan. So S times C2, just from here, is going to be M2 times S plus E2. And we have this additional term, which is E1 times C2, which we just sort of keep carrying around because, well, we don't know how to break it any further. And what we get in the end is M1, so M1 times M2 times S, plus M1 times E2, plus E1 times C2. So we got something that kind of looks like what we had before. So we have M1 times M2 times S, which is sort of our new message times S. But for the noise, well, we get something more complicated than before. We get M1 times E2 plus E1 times C2. It's sort of asymmetric in a sense. You'd get something else if you did it the other way around. And it's a good question whether this thing is going to remain small or not. It really depends on the specific implementation of this scheme. So it seems like our noise is going to grow, and in order to control the growth, in order to make this thing manageable, we really want C2 to be small. And there's sort of many notions of how you can sort of define it in the tightest way. But for us, we're just going to think that we want all of the entries of C2 to be really small. And if that was the case, then really we could argue that C2 does not make this part of the noise too large. So it seems like it could work if we had an approximate eigenvector encryption scheme. Then we should be able to get at least some sort of homomorphism. And now let's see how to actually construct a scheme like that. And we're going to use. Oh, and yeah, I should say that you can also do the opposite operation. I guess I did. So we're going to use the learning with errors assumption, which had been very, very useful in cryptography since Regev introduced it in 2005, and actually also a little before without knowing. And this assumption says the following. I guess the intuitive statement is to say that if you have random noisy linear equations modulo an integer, then they're going to be computationally indistinguishable from uniform. And to be a little more concrete, what we have is the setting is the following. So we think about a uniform matrix A, and A is I guess wide and short. It's n by m, so n is this dimension and capital M is this dimension. So this is just going to be a uniform matrix, and we're thinking about this matrix as a sequence of coefficients for linear equations. What does that mean? We have a secret n-dimensional vector S, and we take the product of the vector S and the matrix A. So this actually gives us sort of a sequence of linear equations where the coefficients of the equations are the columns of A, and the variables are the components of the vector S. So we take these linear equations, and actually we add some noise to them. And this noise is just going to be a vector of small entries. In order to get the tightest reduction, you may have heard that you want to take this vector to be drawn from a Gaussian distribution or a discrete Gaussian distribution. But for the purpose of this talk, we're not going to care about it. We're just going to think about this as a vector of very short elements. In particular, each element in this vector is going to be smaller in absolute value than some alpha times q, and alpha is going to be really, really tiny, and we're going to see how tiny it needs to be later on. So we take these these random linear equations, we add noise to them, and we get some vector b. What does it mean to be indistinguishable from uniform? Well, so we have this b, which equals to s times a plus noise. And now let's think about the joint distribution of this uniform matrix A and the vector b. It's not hard to see that this distribution is going to be statistically far from uniform, at least if this alpha is small enough. And to see this, just think about, so S times A is going to be a random element in the row span of A. And this row span of A is going to be, since it's wide and short, this is just a hyperplane in ZQ to the M. So we have this fairly low dimensional hyperplane, and we take a random point in this hyperplane. Obviously, if I give you these two things, it's going to be statistically far from uniform and computationally distinguishable from uniform. But turns out that if you just add some noise, so if you think about this like as a fuzzy hyperplane in this high dimensional space, well, it's still going to be statistically far from uniform, but the learning with errors assumption is that this is actually going to be computationally hard to distinguish from just a uniform distribution. So from the case where we sampled both A and B just uniformly and independently. So this is pretty great, and we even think that it's true. In particular, we actually have like strong reasons to believe that it's true. It had been shown in a sequence of work, starting with this work of Regev, that if you can distinguish this from uniform, then well, really at the very, I'm saying the statement very roughly, then this is at least as hard as approximating short vector problems in the n-dimensional lattices. And this is true in the worst case. So this is an average case problem. It talks about distributions. Everything here is drawn from some distributions. And yet, if you're able to solve this average case problem, so if you're able to distinguish these two distributions, you are actually able to approximate approximate short vectors in really any lattice that I give you, any n-dimensional lattice that I give you. And the approximation factor, as you would expect, sort of deteriorates as alpha goes down. So obviously, if alpha was like, I guess, 1 over infinity or 0, then this would easily be distinguishable. This problem becomes hard. And as alpha times q becomes bigger, this problem becomes harder. From this point on, we're not going to be concerned about whether this is hard or not, and we'll feel pretty confident to use this as our hardest assumption. And I actually want to sort of rearrange the notation. It'll be more convenient for me to just think about the matrix that consists of minus a and b. And I hope this is not going to be too confusing, but from now on, I'm just going to call this A. So my new A is just going to be what used to be minus A and B. This is sort of the traditional notation, but this new one is going to be more convenient for me. And what we have for this new matrix is that if I multiply it by S concatenated with 1, then really what we get here is B minus S times A. And B minus S times A is going to be this short vector. So what we actually have, so this new form of LWE says that we have a matrix A. We can generate a matrix A and a vector S such that S times A equals to this very short vector. So obviously A is very far from being uniform. But on the other hand, if I just show you A itself without telling you that I have the secret key, this is going to be computationally indistinguishable from uniform. So from now on, we're just going to think about being able to generate matrices like this, and I showed you that this follows from the learning with errors assumption. All right. So how do we get an encryption scheme from this LWE structure? This is, I guess, based on Regev's first paper, and also on this paper by Applebaum, Cash, Packard, and Sahai, that gave an extension that will be very useful for us. So, as you would guess, the public key is just going to be my matrix A, and my secret key is just going to be this secret vector S. How do I encrypt? I take my matrix, and I multiply it by a uniform binary vector. So this is just now going to be a 0, 1 vector. Even though we think about it modulo q, it's still only going to contain zeros and ones. And it's going to be m-dimensional. So I multiply on the right here, and I add some other value y, and this value is actually going to be the encoding of the message. So here is where the sort of message that I'm encrypting going to come into the play. I'm not going to tell you how exactly at this point. So I'm taking this AR plus y, and I get my ciphertext. So my ciphertext is this C sub y. And to see why this is a secure encryption scheme, well, in the eyes of an attacker who doesn't see the secret key, only the public key, this matrix A is just a uniform matrix. It's computationally indistinguishable from uniform. And had it really been a uniform matrix, we get from the leftover hash lemma that A times R, even given A, is going to be statistically close to uniform and independent of A. And therefore, we can conclude that the joint distribution of the ciphertext and the public key and the ciphertext, regardless of what this vector y is going to be computationally indistinguishable from being jointly uniform, so long as m is large enough. And this is going to give us security for this scheme. All right, good. So we have a secure scheme, but sort of we kind of want to also be able to decrypt. So what happens when we try to decrypt these ciphertexts? So hopefully this sort of Lego presentation sort of hints that the way to decrypt will be to just take the secret key and multiply it with the ciphertext, if nothing else, just because the dimensions match. So what happens when we do it? We take the secret key times the ciphertext. Well, what is this ciphertext? It's A times R plus Y. So I'm taking the secret key and multiplying it by A times R. So we know that S times A is this small noise vector. So when we multiply by R, we're going to get really the inner product of the vector eta and the vector r. Both of these are small vectors. Eta, remember, we said that it's the absolute values are at most alpha times q, and r, we just chose it to be 0, 1, so it really has short entries. So we're going to get something that is pretty small. It's going to be a noise value. But the second part, perhaps more interesting, is again we take S times the ciphertext, so this part we took care of. But now we have the vector y, and what we get is the inner product of our secret key and this encoding of the message y. And what you get is sort of an approximate way to encrypt this inner product of secret key times y for any y that I want, and I can do that without knowing S itself. So I can actually encrypt some function of the secret key without knowing what the secret key is. Okay, so this perhaps seems weird, and for one thing, you'd want to perhaps see how you can just encrypt messages 0 and 1. So let me show you like a very rudimentary way to do it. So let's just think that when I want to encrypt a 0, I'm just going to take this vector y to be 0. And when I want to encrypt a 1, I'm going to take this to be a completely random vector. In that case, when I try to decrypt, if y equals to 0, then I'm really only going to get this small noise. But if y is uniform, then with very high probability, I'm not going to get something that is small. Of course, there are much better ways to encrypt the scheme, but I don't want to get into that. We'll see a cooler way to encrypt with additional properties. But this is sort of the basic encryption scheme that we're going to use. And actually, we're going to generalize it a bit, because if we can encrypt with respect to vectors, why not do it for matrices? So what we're going to do is actually take these y's, instead of being just vectors, we're going to sort of expand them to matrices. So to encrypt, our encryption is just going to look like a bunch of the previous encryptions. So we're going to get a ciphertext, which is a matrix, but each of the columns of the matrix is just like a column ciphertext like we saw in the previous slide. So instead of multiplying by one row vector that is 0, 1, we're going to multiply by capital N such vectors. So we're going to get A times R plus some matrix Y. And now our message needs to be encoded in this small n plus 1 times capital N size matrix. So if we were wasteful before, just sort of encrypting one bit in a vector, now we're going to be even more wasteful and just encrypt. In order to encrypt one bit, we're actually going to have this entire ciphertext of this matrix of a ciphertext. But so this I claim is going to be a step in the right direction, because in the end we want to implement this approximate eigenvector method, and for that we do need our ciphertext to be matrices. All right, so the decryption is going to work in exactly the same way. We're just going to get, instead of just getting one entry, we're going to get a vector of entries, each of which is a decryption of the respective column. So I'm going to take S times CY, and what I'm going to get is this noise vector eta times R. And again, this eta is short, and this R is a matrix of 0, 1 entries, and therefore this is just going to be a vector of small entries. This is our noise vector, plus vector S times the matrix Y, which encodes the message. All right, good. How do we use this to get the approximate eigenvector? Well, we need two things. So first of all, we need to choose y as a function of our message m in a way that will allow us to do all these eigenvector tricks. So I claim that this is going to be the easier task. Or I guess this is going to be the task that we're going to see second. But first I want to sort of handle this trying to get the entries to be small. So remember that we needed our scheme to have small entries in order for this noise when we do multiplication to not grow by too much. So in this particular scheme that we're thinking about, this ciphertext matrix actually looks like a uniform matrix in ZQ. So obviously it's not going to have small entries. So we need to come up with a way to take matrices that have large entries and make them into matrices that have small entries. And the way I usually describe it is the second stupidest thing that you can think of. So the first stupidest thing is that, well, if I want to take a big number and making it into a small number, well, the first stupidest thing would be to just scale it down. But this doesn't work in this case because, in a sense, scaling down is equivalent to doing nothing. But perhaps the second stupidest thing would be to just take this number and break it into, I guess, its binary digits. Each binary digit is small, so everything is small. So this is exactly what we're going to do. We're going to take this matrix, this ciphertext matrix that we started with, and break each of its entries into its binary representation. So let's take an example. Thinking about the matrix 3514 mod 8. And the binary decomposition of this matrix, well, 3 is just 0, 1, 1, 1 is 0, 0, 1, 5 is 1, 0, 1, and 4 is 1, 0, 0. Done. I got a matrix. Well, it's kind of bigger than or taller than the original matrix, but maybe that's okay. And it only has small entries. So this is what we wanted. But on the other hand, this is the second stupidest thing that you can come up with. You lose all the structure that you had here. I mean, all the linear algebraic structure that you had seems to have been gone. What does it mean to take this secret vector S times this bit matrix? That's kind of weird. So the cool thing about this is that even though this operation is in particular nonlinear, the inverse of this, I claim, is going to be a linear operation, and this is going to be extremely useful. So I claim that giving this bit decomposition of C, I can actually multiply it by some red matrix and get C back. And just maybe take a minute to think about how you do it. How do you sort of take the binary representation and convert it back into the number? This is really a linear operation. So this matrix is just going to look like, the powers of 2, 4 to 1, 4 to 1 on the diagonal, and 0 everywhere else. So this is often referred to as the gadget matrix, and sometimes you change the orders of the columns, and this still works. It just corresponds to different binary representation. So when you take this binary decomposition and multiply it by the gadget matrix, you really get your original matrix back. So this may not be as stupid as we thought, because the linear structure doesn't really go away. And just to sort of emphasize that this operation is really sort of the inverse of a linear operation, this is usually denoted by G inverse of C. So G is a matrix, but G inverse is a function. So G inverse is like an operator, a nonlinear operator that works on matrices. But its left inverse is just a matrix, and this notation is going to be extremely convenient, as we will see in the next talks. So what we have here is that, well, if we thought about trying to decrypt a ciphertext, a normal ciphertext, so taking S times C, then this is exactly equivalent to taking S times G, so S times the gadget matrix, times G inverse of C. So in a sense, we have a linear way to sort of treat these binary decompositions of ciphertext. Good. So this problem is solved. We are able to represent matrices in a short way. And just to sort of point your attention, I can generate this gadget matrix for any number of rows that I want. And the property that it's going to have is that if it has k rows, then it's going to have k times log q columns. So the proportions are sort of kept. So now let's actually see this the final encryption scheme. So remember, our public key is this matrix A, which is wide and short. Our secret key is a vector, and we have this property that S times A is short, is this short vector eta. Now to encrypt a message M with randomness R, so this R is just going to be this big 0, 1 matrix that we saw before. What we do is take A times R plus M times G. So my Y matrix, the matrix that I was alluding to before, is really just taking my message M and multiplying it with the gadget matrix G. This is going to be, so the dimensions are going to be really the same as the dimensions of the gadget matrix. It's going to be n plus 1 by capital N, which is n plus 1 log Q. All right, so why does this work? Why is M times G the right choice for the matrix Y for the encryption? Well, what we have for this type of encryptions is that when I sort of take my ciphertext and multiply it by the secret key, which is going to be an essential part of our decryption process, what we get is a small vector E, like we saw before. This is what you always get. And then you get S times the matrix Y, which in this case is the same as the message M, which I can move to the side, times S times G. And perhaps at first glance, it's not clear what's the eigenvector here, and it's not clear where's the short matrix, but I can actually sort of present it in a slightly different way. So S times C is really just S times G inverse of C, which is, we just saw that. And we get that SG times G inverse of C is small noise plus M times SG. So if you want to sort of go back to this to the eigenvector intuition, then you can think that about S times G as being an approximate eigenvector for this G inverse of C matrix, which is both going to be square now because, well, the proportion magically just match. When you take G inverse, it's not magic. It has to work. The G inverse just sort of makes this ciphertext matrix square. So it's going to be square, and it's going to have an approximate eigenvector, which is S times G. But actually, this intuition that was pretty useful in getting us to this point, we can abandon it from this point and on. And all that I'm going to care about is that I'm getting this encryption scheme for which this invariant holds. So my ciphertexts are these matrices such that S times C equals M times SG plus small noise. And now let's see how to do, well, first of all, decryption. So I didn't show you how to decrypt these ciphertexts. It doesn't matter that much, but let's see it anyway. So in order to decrypt the ciphertext C, I'm going to compute S times C. It's going to give me this thing, but in order to extract M, I'm going to do this little trick. I'm going to multiply by G inverse of this vector. What is this vector? Well, U n plus 1 is just a unit vector. It's 0, 0, 0, 0, and 1 in the end. And I'm just multiplying it by the scalar Q over 2. So a nice property, why did I choose this vector? So perhaps you remember ages ago when we sort of defined this vector S, we had a slightly shorter S and we added 1 in the end. This means that the inner product of this U with our vector S is going to be 1. So this is a vector that is sort of the right inverse of our secret key. So what happens when we do this multiplication? Well, we get E times the noise E times this G inverse of something. We know that this is kind of small, so we take a small noise, multiply it by G inverse, that's fine. And this is going to be plus M times SG times this G inverse. We know that G and G inverse go away. So at this point, this becomes sort of, this is where the fun happens. Whenever we see G and G inverse, we can just sort of remove both of them. And what we get is something small plus Q over 2 times M times inner product of S and U, which is just 1, so we can just remove it. So what you get is, well, if M equals 0, then you get something really small. And if M equals 1, then you get Q over 2, which is really sort of the largest element mod Q, plus something small. So it's very easy to distinguish these two apart. And this is how the scheme is decrypted. And now let's see how to do homomorphic operations. So again, the invariant that we want to keep throughout the homomorphic evaluation is that we want to have ciphertext such that S times C equals E plus MSG. So long as this holds, we can decrypt. That's what we saw. So long as this holds and the noise is small enough. So in order to do homomorphic multiplication, what we're going to do is we're going to take, we have C1 and C2, and we take C1. Now we don't multiply it by C2, just the dimensions don't work. So we take C1, which kind of looks like this, and multiply it by G inverse of C2, which luckily both has the right dimensions, so it's a square matrix, and it has short entries, which is going to be very useful. And let's see that we get this invariant that we started with. So we have S times C1 times G inverse C2. S times C1 is just E1 plus M1 SG. Gets multiplied by G inverse of C2. So we get E1 times C2. So G inverse C2, sorry. So E1 is going to be fairly small, hopefully. And G inverse is just going to be a 0-1 matrix. So we remain in the pretty small domain. Times M1 SG times G inverse of C2. So now the way the scheme had been constructed sort of gives us that this S times G, which just seemed disruptive, now just cancels out with this G inverse. And what we get is E1 G inverse C2 plus M1 SC2. So G and G inverse goes away. S times C2, we know how to expand it further. We just have M1 times E2 plus N2 SG. That's again coming from up here. So just opening the parentheses and putting everything together, well, we see that we have M1 from here, M2 from here, SG. So we have M1, M2, SG. So this is good. This is the output of the multiplication operation. Now, what do we have as the noise? Well, we have M1 times E2 that comes from here. So this is going to be E2 is kind of small, and M1 is 0, 1, so this remains pretty small. But that was the part that we sort of were pretty relaxed about also from before. What used to be the bad part, we used to have E1 times C2 here in the sort of naive approach, but now we have E1 times G inverse of C2, and this G inverse really has just small entries. And indeed, this new noise is going to be pretty small. We can bound it relative to the noises that we started with. So this is how you do multiplication. So if you didn't sort of follow all the specific derivation, the multiplication is defined like this. And when you sort of open everything up, you really get the same invariant that we started with, except the noise is going to be this E1 G inverse E2 plus M1 E2, and I'm almost done. So the first thing I wanted to point out is that I did multiplication, but actually doing NAND is just as easy. We just take this gadget matrix G minus the multiplication. So it's not hard to verify that taking G minus ciphertext is equivalent to making the message into 1 minus M. So 1 minus multiplication gives us NAND, and this whole thing works exactly the same way. In fact, the noise really is the noise expression is the same in both cases. This G inverse is just going to affect what happens here. So what we get is that when we do multiplication, or when we do a NAND, the basic operation for our circuit, our noise is going to grow as follows. So I'm giving a very loose analysis here. You can be much tighter and get somewhat better a somewhat better expression. And I see that I also swapped E1 and E2 here. I'm sorry. So we have E1 that gets multiplied by this G inverse. Let's just say that this grows the norm by a factor of n, the dimension of the matrix. On average, it's going to be much better. And we have this should be E2 times M1, and M1 is just 0, 1. So in the end, if we started with some E1, E2 with norm E1 and norm E2, what you get in the end is at most an increase of an n plus 1 factor in the amplitude of the noise. And is it good or bad? Well, it depends on your perspective. It's not as good as what we had for addition, which was just a constant increase. But on the other hand, it's much better than what you'd get trivially. And in fact, it's good enough to get homomorphic, non-trivial homomorphic capabilities. And I just want to point out that this noise expression, it's perhaps very strange, but one property that we'll see that is going to become very useful is that this is actually a linear operation on the original noises, on E1 and E2, and linear in the sense that if I know the ciphertext or the ciphertext C2 and the message M1, then I sort of know how my old noise is going to progress into the new noise. And well, if you know the message, then this doesn't make much sense in terms of homomorphic encryption. But we'll see that in other cases, it is going to sort of make sense to know both the ciphertext and the message, but actually not the noise. So this is sort of just a preview. But just to wrap up, we showed how to do one gate. If we want to evaluate an entire circuit, then with each level of the homomorphic evaluation, our noise grows by a factor of this n+1, say. And when we evaluate the depth D circuit, we get a noise growth of something like n to the power d. And n is like a polynomial in our security parameter, or size of the keys of our scheme, and so forth. So in order to make this decryptable, we need the amplitude of the noise to be much smaller than q, or at least somewhat smaller than q. So we need this alpha to be really small, to be something smaller than 1 over n to the d. So it grows exponentially with the depth of the circuit that we want to evaluate. And again, whether this is good or bad is a matter of perspective. It's almost the best that we can get, and it's good enough to get practically any notion of homomorphism that we want. So just to wrap up, I'm a little behind, I see. We showed the encryption scheme. The way you encrypt is you take the public key matrix A, multiply it by 0, 1 matrix R, plus mg. This invariant is that when you take your secret key times C, you get noise plus message times SG. To do homomorphic evaluation, I just take two ciphertext C1 and C2, do the binary decomposition, and multiply. If I want NAND, I take G minus this whole thing, and this just gives us homomorphism. We only saw how to do bounded depth because at some point your noise is going to grow too much and you're not going to be able to decrypt. This is solvable, but not in this talk. So one way to do it is to sort of choose the parameters appropriately. So if I know D ahead of time, then I can choose the parameters for this LWE instance so that the scheme is secure under sub-exponential approximation to lattice problems. So fairly strong assumption. Gentry presented like a great idea called bootstrapping. So the bootstrapping procedure actually allows you to get a scheme for any depth without compromising on the parameters of the LWE instance. So these parameters are not going to grow, but something else will grow, the size of the public key, but in a way that does not affect the hardness. And actually, using this approach, you can actually get homomorphic encryption based on a much weaker assumption, namely the hardness of approximating lattice problems to within a polynomial factor in the dimension. And actually, but still there's this annoying order of quantifiers that I need to know the depth, and only then I can give you a scheme. And again, this is shown by Gentry, that if you combine this bootstrapping with an additional assumption, which we don't know if it's true or not, it's the circular security of this encryption scheme. So this is an additional security requirement of the scheme. Then you can really get just one scheme that works for any depth circuit, and this will really give you the full-fledged, fully homomorphic encryption. So really, I'm already behind. Let's get Daniel to tell us about signatures. Thanks.